Hello everyone, my name is Cihangir Tezcan and I'm an assistant professor at Department of Cybersecurity. This is my first cryptology talk for the course CSEC 591. So let's start. Historical ciphers mostly operate on letters since they are pen and paper methods, and when working with digital data we can represent letters, numbers, symbols, etc. as strings of bits. Thus, the communicating parties must first agree on an encoding. So when I teach applied cryptology, I also give examples about historical ciphers and how you do operations on letters by using pen and paper methods. But since we moved on to a digital age, now we have to represent data in a digital way. So encoding is actually the language the machines are going to speak, so that in order to understand each other, we have to first agree on the encoding. So here's an example from the ASCII code. I think you're familiar with it. So we represent the character by a byte. A byte consists of 8 bits, so you can represent 2 to the 8 different characters with a single byte. This is why this list starts from 0 to 255. And capital letters start from here, and small letters go here, and so on. So, of course, these are the integer representation, these are the hexadecimal representation, and so on. So, we are just assuming that in order to perform cryptographic operations, we first assume that everybody speaks the same language, so they are agreed upon an encoding first. So, of course, you might think that this is obvious, but as you might know, we're still having problems with Turkish characters when people insist on using ASCII table but use Turkish characters. Then Turkish characters cause a problem. This is mostly happens in databases when they create the table, but in a way that the data is stored in using the ASCII encoding. So we're just assuming that we can represent every character in terms of bits in some way. So from this point on, we will work on bits and explain how cryptographic algorithms work and how we do perform encryption and decryption and so on. So cryptography actually solves a lot of problems. Cryptography solves confidentiality problem. This is mostly done by encryption. So we have many different encryption algorithms. Symmetric key encryption algorithms generally categorized as block ciphers and stream ciphers. But we have also asymmetric key cryptography algorithms like RSA or Al-Gamal and so on. But we also have authenticated encryption algorithms, which also gives you encryption, so confidentiality. Cryptography also solves the problem of data authentication. For this case, you can use hash functions, message authentication codes, or again, authenticated encryption. Other problems we solve are entity authentication or origin non-repudiation, which is actually can be solved by digital signatures and so on. So this is actually this was to show you the big picture, but it is still not the whole picture. Cryptography has a lot of different areas, like proof of security, quantum cryptography, or randomness are other areas of cryptography that we deal with. So the picture is really big, but depending on which problem we are considering, we focus on a smaller part of it. And today I'm going to talk about block ciphers and show you how it solves the confidentiality problem. So let's start with what a cipher or a crypto system is. So plaintext is what you want to protect. So this is the thing that you want to protect. It can be a file on your computer, it can be an SMS message that you are sending, or maybe it is this video that I'm going to send you, but in an encrypted way. So I want to, I don't want people to see this plain text. So what a crypto system does is that it is actually a pair of algorithms that performs encryption and decryption. So it takes the plain text and performs an encryption operation and turns into something that is not understandable by anybody else. So it doesn't give any information about the plain text itself. So ciphertext is the encrypted version of the plain text, and it should look like a random sequence. So it should look like random zeros and ones. And decryption operation turns ciphertext back into plaintext. So this is what a cryptosystem or a cipher is. So in the symmetric cryptosystems, you have a secret key, and you use the secret key information when you are performing encryption and decryption. So if you have this secret information and give it to the people that you are going to communicate, this way each parties can encrypt and decrypt each message, and you can send the ciphertext through any communication channel you want. And here, this is actually the important thing. In cryptography, we are assuming that the communication channel is insecure. So this is the main idea. So if you're, for instance, if you're using a wired communication, for instance, if you are visiting a web page from Turkey and the web page is in the United States, so you are actually sending data from here to there. So at any point in time, somebody listen to that communication. If it is a wireless communication, it is even easier. Somebody close to you with an antenna can listen to the signals you're sending. So we are always assuming that the attacker can always capture the ciphertext because the channel is insecure. So we are trying to provide security in an insecure channel, and this is a way how you can do it. You encrypt your data and send the ciphertext. Everybody captures the ciphertext, but they cannot turn it to the plaintext, but only the people who has the secret key information can do it. So that is the main idea. So how the block ciphers works is as follows. Block ciphers operate on b-bit blocks of data. Plaintext is divided into b-bit blocks. Each block is encrypted by a k-bit secret key to produce b-bit output. Output blocks form the ciphertext. And how you do it, I will actually mention, because this is actually the, I mean, if you're encrypting more than a single block, then you have to decide how you will perform the operation on them. So this is actually called mode of operation, and final slides will be about that. But a block cipher with this definition and a block cipher and the chosen key is actually a permutation from 2B elements to the 2B elements. And B here is the block size. Nowadays we use 64 or 128 bits, which is 8 bytes or 16 bytes. And for secret key, we recommend using 128 bits or something larger. Smaller than this actually can cause problems. Maybe not today, but in the future. I will also talk about why this size is important. So let me give you an example of a block cipher. Block ciphers can be designed in different ways, and substitution permutation network versions is just one of them. Another famous one is phase-style. I will also give an example. So idea is as follows. You have a secret key here, and you have the plaintext that you are going to encrypt. So assume that this is a single block. So there is a b-bit message that you want to encrypt, and you have the secret key. And substitution permutation network works like this. So you have a key schedule algorithm that takes the key and provides round keys from the secret key information. So initially you add this information to your plaintext. Maybe you just add it bit by bit. Then you perform a substitution operation, which actually provides a confusion. Then you perform a permutation layer, and actually this is a single round. So each round consists of substitution, permutation, and round key. So you repeat this process many times, and at the end you provide the ciphertext. So as you can see, person who captures the ciphertext and who also knows the operations that are performed here, who knows the algorithm, cannot go from here to here, because initially they have to know what the round key is to go from here to here and move upwards. Even the person captures the plaintext and the corresponding ciphertext, with these two knowledge, they cannot go from here to key. They cannot capture the key because the algorithm, the intermediate values, you cannot obtain them from this information. So if it is a good design, then capturing plaintext and the ciphertext would not leak the key material. That is the main idea. So let me give you a concrete example. This is a present cipher. This is actually ISO standard for lightweight cryptography. So for small devices, especially on hardware, this is suggested by ISO. So it is a standard. So a single round of present is in this picture. So it is a very simple design. And block size is 64 bits. Key length depends on you. You can choose either 80 bits or 128 bits. But there's no point of choosing this when you can choose this actually, because it wouldn't cause, it will just cause a negligible performance slowdown, so it is not important. And the cipher is designed as 31 rounds. So this is the idea. You have this picture, so this is a single round, and each line, if you count it, you will see that there are 64 lines here, since the block size is 64 bits, so I'm representing every bit by a single line here. Initial operation is the XOR operation, where you add your round key bit by bit to the plaintext block. So this is actually an addition operation in modulo 2. We call it XOR operation, and it is represented like this. So your initial operation is just adding your round key to the input block. Then you gather this 64 bits into 4 bits parts, and you put them into a table that we call S box, substitution box, and provide 4-bit output. So it takes 4-bit input and 4-bit output. So this S is defined like this. So in the hexadecimal notation, for instance, if all of the 4 bits are 0, in hexadecimal notation it is 0, and it says that the output is C. So C is actually 12 if you turn it into integer. And if you assume that the rightmost bit is the least significant bit, and it is the case for this cipher, C is in the binary notation 1, 1, 0, 0. So if you put all zeros as the input, you will get 1, 1, 0, 0. So you perform this operation 16 times in parallel. So you perform this S-box operation 16 times. So this is your substitution layer. So this is actually causes a confusion, and this is actually where the security of the cipher comes from. Now you need to cause some diffusion. So a bit here should affect other parts of the cipher. So for this reason, you perform a permutation. For instance, this bit is kept here and stays at the same place, but this one goes here, this one goes there, and so on. So this is a single round. As you can see, it says that the cipher is 31 rounds. So take this picture, put it again, put it here again, and so on until 31 times. And finally, at the end, you will add a final round key XOR here. So after that operation, you will provide the ciphertext block. As you can see, you're performing a lot of operations here, which causes some confusion and diffusion. So if you go back to the picture here, anybody capturing the ciphertext and knowing the present algorithm without the knowledge of the key cannot go from here to here, or again, if they know the plaintext and the ciphertext block, it wouldn't leak any information about the key. So a concrete example is like this. But if we want to give a more historical example, the most famous one is data encryption standard. Of course, it is no longer a standard, but for some reason people think it is and still using it, but you should avoid using it. It was designed by IBM in 1970s based on an earlier design by Festa. So in 1976, NSA tweaked some parts of the cipher and made it, and NIST made it a standard. In this algorithm, the block size is again 64 bits, but key length is really short. It is 56-bit and rounds are 16. But currently known as data encryption algorithm, DEA, since it is no longer a standard. And it became useless after 1990 since its short key is susceptible to brute force attacks. So it's pictured like this. So in this case, it is a face-down cipher. So I just wanted to show you this picture to show you how a face-down cipher works. So plaintext block is divided into two parts, left and right. So right part is becomes the next, in the next round becomes the left part. So that is the idea. Right part actually, without any modification, becomes the left part. But right part also put inside the round function, and there are some operations here. like substitution and permutation, similar to present, and the output is XOR the left part. So at a single round, you modify the left part, but nothing happens to right. But then you take right and make it left, and this output becomes right. And in the next round, this unmodified part is modified, and so on and so forth. And you have a key and key schedule algorithm is just permutation and rotation operations. There's no need to go into detail, but this is another example for a block cipher. Of course, I told you that this is no longer used because the key size is short. Why I say this as follows: an attacker that captures a single ciphertext can try to decrypt it with every possible key to check if it provides a meaningful plaintext. Such an attack is called exhaustive search or brute force attack. So if we go back to picture, you captured some ciphertext and you don't know the key, but assume that it is all 0, perform the decryption operation and check if the plaintext is something meaningful. If it is not, increment this by 1 and do this operation again and again until you try every key. But since the key is k-bit, this means that in the worst case scenario, you have to perform 2 to the k encryptions or decryptions if you're doing in the other way around. Important thing is that this is not a weakness of the cipher. Exhaustive search is a generic attack, so it is valid for every cipher because somebody can try every possible key anytime. So security of a block cipher is upper bounded by exhaustive search, which is 2 to the k encryption. So since this has a 56-bit key, you can break this by performing 2 to the 56 encryptions. Before showing how easy it is, I will mention the current standard. Advanced encryption standard replaced this. There was a competition which started a few years before 2001 actually, but the Rindell algorithm designed by John Damon and Vincent Raymond won this competition, and it was standardized in 2001. There were other finalists: Serpent, Twofish, RC6, and Mars. You can see these names if you use some open source software like OpenSSL and so on. As far as we know, they're still secure, but AS won the competition. And its block size is now larger, 16 bytes or 128 bits. And you're allowed to choose your key length depending on which kind of security you need. For personal security, this is enough. But for military grade security, you have to choose your key length longer. And depending on your choice, the number of rounds increases. And for larger key size, you have more rounds, so it is a little bit slower. And as far as we know, any attack that is on the cipher currently are ineffective. So we can use it in confidence. So question is, how hard is the exhaustive search? So I told you that this has 56-bit keys. So in order to break this, I have to perform 2 to the 56 operations, which is this many encryption operations. And for present, we said that it has, you can choose key size is 80-bit, and it requires this many encryptions. And for 228, it is this for AES. And for other AES key lengths, it is this. As you can see, it is a very huge number. As far as I know, it is around the number of atoms in the universe. So it is a really huge number. And we are not assuming that anybody can perform this many operations. So how do you perform the exhaustive search attack? Easiest thing you can get a hold of is CPUs. Everybody almost have more than one computer now, laptop and desktop. So you can use your CPU, and it comes with many cores now. You can use all of your cores to perform encryptions. And generally, a CPU core can perform around 2 to the 20 encryption operations, depending on the clock speed, of course. So, and a year has like 2 to the 27 seconds in a year. So it will take a few years for you to break this using a single computer. But of course, this means that if you use a lot of computers, you can break it in less than a year. But GPUs are better in parallelizable algorithms, and exhaustive search attack is parallelizable because you're just simply trying a different key but performing the same operation. So GPUs can get maybe 10 times, sometimes 100 times faster results than CPUs in these parallelizable algorithms. And a GPU can perform around 2 to the 33 encryption operations in a second. A modern GPU can do that. So it will take like a few months to break this in a single GPU. But of course, if you have a lot of GPUs or a few people can get together, this means that you can break this in a few seconds or a few hours. Another thing is the FPGAs, field programmable gate arrays. These hardwares are also good in performing parallel operations, but it requires a little bit more special to use them. But when you burn these FPGAs, your algorithm on the silicon, they became dedicated hardware. They can only perform the implemented algorithm, but they become very cost effective. So if you burn your this algorithm into ASIC, that can probably break ASIC, this in a few seconds. But the important thing is that if the technology becomes really good, and you assume that you can you can perform this many operations, so you can break present actually in a second. Assume this is the case. So you have a lot of computational devices, and you can perform 2 to the 80 encryption operations in a second. This means that, as I told you, a year has like 2 to the 27 seconds. So this means that in a year you can perform 2 to the 107 operations. So even with that power, in order to perform exhaustive search on AES, you would need like 2 to the 20 or 21 years, which is, I think, more than 2 million years, right? So even if you can have such a good technology, the performing exhaustive search on these key lengths would not be easy. So this is why we are assuming that these key lengths are secure enough, but using something shorter than these would not give you much security. An example is as follows. I tried to perform exhaustive search on present with 80-bit key. So I use my laptop and my desktop. This is actually the results are from 5 or 6 years before. So I realized that my laptop can perform 15 million encryptions per second, and desktop is twice fast. It is 31 million encryptions. But I use also the GPUs on these devices. Again, this laptop is from 2010, but it comes with 96 core, and I could perform almost same as my desktop CPU. So I could perform like this many encryptions in a second. But when I use something better as a GPU, the speed up was really huge. I could perform 452 million encryptions in a second. Of course, if I use this GPU alone, it will take me 84 million years to break the cipher. But currently I have better GPUs with RTX 2070 Super. I could perform more than 800 million encryptions per second. So I reduced this number to 40 million. With newer GPUs, you can reduce it to 20 million. And you might say that, okay, I'm not planning to live that long. But of course, this means that if 20 million gamers get together and try to break your cipher, they could do it. So this is the idea behind it, actually. So this is why, of course, this is on GPUs. Maybe if you have ASIC, then you can break the cipher even better. So this is why we are not recommending usage of 80-bit keys. Move on to 128-bit key and you would be secure enough.